Okay, so we had done some work on relations, and we're going to pick up where we left off. Thanks. We're going to pick up where we left off on that. Finish this section on relations, talk about a special kind of relation called a partial ordering, or in other words, look at partially ordered sets. And then as time allows, so that section on partially ordered sets is pretty short. So then as time allows, we will spend some time on equivalence relations. We'll see where we're at. Just a couple comments about submitting your assignments. If you're going to submit them online, and some of these actually apply regardless, neatness counts, right? It needs to be legible and organized. There has to be like a flow, some clarity to what you're doing. Space out your solutions, so there's space for me to write comments. So don't finish a problem and then on the very next line start another one. Actually, leave some space. If you're submitting online, use Adobe Scan or Cam Scanner or whatever, an actual scanner or some other app. But the idea is you can create a single PDF that is far preferable to uploading several single files. And then just a reminder that we want pages that aren't just photos converted to PDF format, but are nice, clear, high contrast pages. Oh, and the assignment sheet should be a cover sheet. Also, write your name on it. It's a really nice touch, because once I download them, it's hard for me to remember. Sometimes I have to go back and see, who uploaded this file, and that takes time. I should have those assignments that you turned in back to you for Wednesday. That's my goal. Before we start, before we pick up where we left off, are there questions from last time? Okay. All right. Let's see where we were. So we had just had a lot of fun writing proofs about relations and seeing, if a relation has a particular property. If a relation doesn't have a property, we just needed to find a particular instance where that property didn't hold. That was enough to say that it doesn't have a property. For example, here we could show that, we were able to show conclusively that this relation was not symmetric just by finding this counterexample. But if you're showing that that a relation has a property, when we showed that it was antisymmetric, we had to construct an argument, right, that was convincing. Some more definitions before we look at how we can sort of visualize what a relation is, kind of abstractly. If we have a relation on a set, so think of a set now as just like a set of ordered pairs, and it's true regardless of how you think of it, but I find this easiest to conceptualize when I think of a relation as a set of ordered pairs. So I have some relation on a set A, and remember that means it's a relation from a set to itself. The reflexive closure, you start with the relation, which may or may not be reflexive. If the relation is already reflexive, then the reflexive closure is just the relation itself. You don't have to make any changes. But if it's not reflexive, just add any of the doubles that it's missing, right? If in this relation, in example 120, suppose the pair 4, 4 wasn't already included. If it was missing 4, 4, then the relation wouldn't be reflexive. But the reflexive closure is just add that pair, it's missing it. If it had that, it would be reflexive, and that's what the reflexive closure is. The symmetric closure is defined analogously. So you see, is it symmetric already? If it is its own reflexive closure. If it's not symmetric, you just see what's missing in order to make this symmetric, and whatever it's missing, you just add that in. Similarly for a transitive closure. Add in whatever ordered pairs might be missing to make it transitive. Here we have a theorem that we're not going to prove, But if we let I be the set of all doubles, then the reflexive closure of a relation is just take that relation and throw in any of the doubles. The symmetric closure is take that relation and throw in any of the reverse pairs, right? That's our inverse is like if you take a relation, just reverse the pairs. That's the inverse. So that'll guarantee that if you have the relation going in one direction, that you have it going in the other. And then the way that the transitive closure is worded is a little weird, but so if R squared is R composed with R, right? So we're not multiplying a relation by itself. That doesn't really make sense. But we can find the composition of R with itself. And then R to the k plus 1 is just R composed with R to the k. This sort of allows you to play leapfrog with the ordered pairs that are in the relation. So it's sort of like a set theoretic way of saying whatever pairs you might need to make it transitive, you're going to throw those in. And it's a recursive process because like once you throw in a pair, like let's say, oh, here we go. I've got an example at the ready. Let's say I have a set that contains the integers 1 through 8. And we have a relation that contains these ordered pairs. 1 is related to 2, 2 is related to 3, and 3 is related to 8. Okay. So note that in this relation, we have 1 is related to 2, and 2 is related to 3. In order, if this were transitive, what would also have to be included if given that those two ordered pairs are in the relation?
1 is related to 3?
Yeah. So with transitive closure, we're going to add in the pair 1 related to 3. Okay. Also, we could look up here and say 2 is related to 3 and 3 is related to 8. So given those pairs, what would we need to add?
2 and 8?
Yep. Okay. Now we're not quite done. So we have, now that we've added these, right? Like these pairs, 1, 3, and 2, 8, like they're in our relation now because we've added them. So now consider the fact that we have 1 is related to 3 and 3 is related to 8. So that's what I mean when I say that this is recursive. Once you've added a pair, you have to go back and see, do I need to add anything more? So if 1 is related to 3 and 3 is related to 8, that means that we also now need to add 1 related to 8. So the transitive closure which maybe I'll call that RT. I'm making up my own notation for that right now, just so you know. We're going to keep the pairs that we had and then add these in. If we wanted the reflexive closure, we just have to add in all the doubles. And I'm going to go back to the original one, not the transitive closure, but like go back to R. The reflexive closure of R, I'm going to start with all I had here. 1, 2, 2, 3, 3, 8. And then I'm just going to add all the doubles. for the symmetric closure of R. Again, I'm going to go back to the original relation as given here. What would we have to add? I'm going to start with what they gave us. All of these closures contain the original relation, so we start with those always. What do we need to add to get the symmetric closure?
2, 1, 3, 2, 8, 3.
Great. Questions on that example?
The only question I have, the one that I emailed you about, was in regards to question 16.
Yep.
It declares the subset, but we're still adding other values, or that's what it looked like in the answer key.
I'm sorry. Your volume got really low there toward the end. Oh, okay.
So question 16, there was a subset given.
Yep.
And then it wanted, I wanted you to fill in the values for the relationships for like A cross C. And in the solutions, I found a couple that were like, oh, those would make sense if the subset was fully, expanded. But I didn't see that in the subset, so I was like, why are those listed as answers?
So which one in particular? Did you get the email that I responded to on some of those?
I got the email, but it was so tricky to piece together.
Okay, so which I forget there one part that you had a particular question about. Like maybe we could just talk about it. Like, did it start with part C or part B?
Let's do part B.
Okay.
SOR.
Okay. Yep. So S composed with R. So they tell us that S contains 610, 611, 710, 813.
Right.
Okay. So 610, 611. Uh, 710, 813.
And R is 1, 7, 4, 6, 5, 6, and 2, 8.
And we want S composed with R.
Okay.
So when we do S composed with R, the inside relation always comes first. So I apply the R relation first. So notice, okay, like R sends 1 to 7, right? But then in S, 7 goes to 10. So that means S composed with R will contain the pair 1, 10. And 1 only goes to 7 in R, and the only thing 7 goes to is 10 in S, and that means in the composition, 1 is related to 10, and that's the only thing 1's related to. Now, let's move on. The next first coordinate we might have is a 4, because that's the next first coordinate in R. 4 goes to 6, right? So to see what 4 might be related to in this composition, I have to see what 6 is related to. Well, 6 is related to both 10 and 11. So 4 goes to 6, 6 goes to 10, that means 4 related to 10. 4 related to 6 and 6 related to 11 means also 4 related to 11.
Okay. Yeah.
Does that make sense?
Oh, yeah.
Cool.
We're on the same page now.
Good. So now the same thing happens with 5, right? 5 goes to 6. So 5's going to go to 10 and 5's going to go to 11. And now is 2 related to anything? Yeah, right, 2 goes to 8, and then 8 goes to 13. In S composed with R, you have to, your first coordinates always come from R, and then you see, where R sends them, and then see if S sends them anywhere, right? So, like, imagine, I'm going to change this slightly, so this is not, now it's not going to match exactly what the practice problem is. But imagine that R also contained, 3, 3, 9. Right? So I would start at 3 and say, oh, okay, 3 goes to 9, and then I look to see what happens to 9 in S. 9 isn't related to anything. And that means that 3 won't be related to anything in the composition. Like, once you see where 3 goes, S, the second coordinate in the R ordered pair has to show up as a first coordinate in S in order for this 3 to map to anything. There can be no dead ends when you're finding a composition. Does that make sense?
Yeah.
Okay. Other questions? Okay. All right. So this section, we're going to stop on a way to kind of visualize a relation. So we could think of them as listing ordered pairs. We could think of them as just describing what it means for one element to be related to another. Like we did that example where we said, oh, X is related to Y if Y is a multiple of X. But we can also visualize them by drawing a graph. And a graph is just a set of vertices and edges that connect vertices. Not like a graph of a function, but just like think of some isolated points. So if we have a set of vertices, here I'll just call them A, B, C, D, E in example 122. A, B, C, D, and E. Then we could think of a relation on this set of vertices by saying, well, 2 vertices are related if they're connected by an edge. So we have a set of edges. And these edges are not directed. Notice that we're using curly braces here and not ordered pairs when we list these edges. So here's an edge set. It says it contains the edge AB. That means that A and B are related. Now, if it doesn't matter the order, right? If this is not directed, right? Like this, it's not an ordered pair. It's just saying they're connected or they're not connected. That means that a graph is a way to visualize a symmetric relation, and in fact also an anti-reflexive, in that we don't allow loops usually when we draw a graph. So we don't have like an edge, a little loop going from the vertex B to itself. So let's finish this graph. So we have the edge AB, we have the edge AE, we have the edge BE, BD, BC, CD. So there's a symmetric anti-reflexive relation, a way to visualize it. If you want to, I mean, so that's like basically what a graph is. You have vertices and edges connecting some of those vertices. You could make a graph that reflects a relation that's not symmetric. And the way you do that is just allow the edges to be directed. So there's some direction. In this one, we have the vertices A, B, and C. And now we have these edges. Now when I am drawing directed edges, I always draw them kind of arced or bowed a little bit because I want to leave space if I need an edge going in the other direction between the same two vertices. So we have an edge from A to A, so we allow loops now. It could be, it could represent a reflexive relation. This one doesn't look like it's reflexive because I only have that one loop. We have an edge going from A to B. We have an edge going from B to C. We have an edge going from C to B. And we have an edge going from C to A. So this is not symmetric because, for example, A is related to B, but B is not related to A in this graph. A digraph is not anti-reflexive, and that's for the simple reason that we allow loops for a digraph. So we could have A related to itself, for example. How we doing?
Wonderful.
Good. Good. Andrew's doing wonderful. I assume you speak for all of Williston, in fact.
Definitely.
Good. Good, good. All right. Okay. So let's talk about a special kind of relation called a partial ordering. So again, we're talking about a relation on a set, not from a set to a different set, but from a set to itself. So if a relation R on A is a partial ordering if it is reflexive, antisymmetric, and transitive. So those properties that we examined last time, we're just going to check, if we want to see if something's a partially ordered set, we just check to see if it has those properties. We check to see if it's reflexive, antisymmetric, and transitive. I don't have to check all four properties. If something is, first of all, I don't need to check if it's symmetric, right? I could check if it's antisymmetric. Second, if I want to know if it's a partially ordered set, if I find that it's not reflexive, then I'm not going to bother checking if it's antisymmetric and transitive, because if it doesn't have one of those properties, it's not a partially ordered set. So we just sort of see what our goal is, right, and see how much work we need to do to accomplish it. So let's start. Let's let C be the set containing the integers 1, 2, and 3. And we're going to begin just with the power set. Does anybody remember what a power set is?
It's like everything, right? They have in common? Or,
What do you mean by have in common?
It would be all the possible combinations of C in this particular case. It would be like 1, 2, 1, 3.
Yeah, right. The set of all of its subsets. And when we list out the power set, when we list out all the subsets, there's one that we always get to list. What is it?
Empty set.
Mm-hmm. So we got that. We got the singletons. We got, how many am I going to be able to list? Does anybody know? Does anybody know without listing them all? Yeah, 8, right? So however big your set is, 2 to that power, so 2 cubed is 8. We should have 8 here. Oops. Those are all the pairs. And then we'll get the set itself. And I think that makes 8. Great. So that was fun. We found the power set. So now what we're going to do is define a relation. So we need the power set to define a relation. So this is the set that we're calling X in this problem. we're going to define a relation on X on this set of subsets by saying that T is related to V if T is a subset of V. So T and V could be any old sets that we included in this power set of C. And we're just saying that two sets are related. T is related to V if T is contained in V. So is the subset containing just 2, is that related to the subset 1, 2? So just keep, look at how it's defined. What do we think? Yes. Sorry, I got, the buttons on the mics here in Randolph are tricky. They don't have the wired mics like you guys have, so sometimes they're slow to turn on. But we did get some input from here in Randolph saying, yeah, it's related, right? The subset containing just 2 is certainly, or the set containing just 2 is a subset of the set containing 1, 2. So this is in the relation because this is a subset of that. Everything in the set containing 2 is in the set containing 1, 2. How about this this next one? Is 2, 3, is that set related to the set 3? No, the order matters here, right? So this is not in the relation because that is not a subset. I mean, 3 is a subset of 2, 3, but the order does matter. We're going to verify that this is, in fact, a partial ordering. So we're going to check. There's only 3 properties we need to check. Is this reflexive? What do you think?
Are you asking if the relation R is reflexive?
We're asking if the relation R is reflexive, yeah. What is it? I guess maybe we'll start. What does it mean to be reflexive?
So you're always related to yourself, so you have like A and B, but you also have A and B, B.
Okay. Yeah, so everything's related to itself. So what does that mean in this relation?
That elements are subsets of themselves.
Yeah, that sets are subsets of themselves.
Yeah, that's not.
Mm-hmm. Yeah, so this is totally reflexive. Every set is a subset of itself. A set contains itself for sure. So yes, every set is a subset of itself. How about antisymmetric? Antisymmetry doesn't mean that it's just not symmetric, right? It means that there's no symmetry at all. With antisymmetry, it just says if you had an instance of symmetry, suppose that A was related to B and B was related to A, then they'd have to be the same set. So what do you think about, what do we think about this relation? Is it antisymmetric, and why or why not? In fact, sometimes I like to... Oh, go ahead. Did I hear...
It's antisymmetric. So symmetry is that you have the mirror object of that element somewhere else. So in this situation, if the first element of the relation, I think I have my terminology right there,
Yep.
Is contained within the second element, then you can't possibly have the reverse of that.
Yeah, yeah. I mean, I think I think you have the right idea. Like, in fact, we could sort of think about, even just think about these examples up here. You know, if I have.
Yeah, the second example there is exactly why it's antisymmetric.
Yeah, I don't know if that's why it's antisymmetric, but I think that we're thinking along the right lines. Like you're saying, we can't really reverse it. If we have a relation going one way, I'm not allowed to reverse it. Yeah, so that's the idea. So now, if we think a relation has a property, we need to justify it. With reflexive, it was easy to justify. Every set contains itself. Done, right? So if I want to show that it's antisymmetric, what we want to do is show that that if I have an instance of symmetry, as it turns out, it just means that was a set related to itself. So let's suppose that T is related to V, so I have T, V in the relation, and I have the relation going the other way, and V is related to T. So if T is related to V, that means that T is a subset of V. And if V is related to T, that means that V must be a subset of T. What does it mean if T is a subset of V and V is a subset of T? Yeah, that's like the definition, right? Of, you know, of, like, it's that definition of what two sets being equal that we use if we're going to show two sets are equal. If each set contains the other, they're the same. So we started out saying, suppose I have an instance of symmetry. Suppose T is related to V and V is related to T. Like, I can reverse it. Must be they were the same set to begin with. So that's what it means to be anti-reflexive.
I don't understand why you need it.
Oh, not anti-reflexive, sorry, anti-symmetric. And then the last property, I'm just going up here to the definition, we got reflexive, anti-symmetric, and then we just need to check transitivity. So is this transitive? Well, let's see. So if we suppose that S is related to T, and that T is related to V, is S related to V? So let's see what, you know, we've written out these relation statements. Let's translate them into what they mean for this relation. If S is related to T, if that's in the relation, that means that S is a subset of T. And if T is related to V, that means that T is a subset of V. What can we say if S is contained in T and T is contained in V? Yeah. Or S must be contained in what? Yeah, V. Yep. Good. S has to be contained in V. So S must be related to V. And that means that the relation is transitive. This is sort of a quick and dirty proof. I didn't leave a lot of room, but I think we got the ideas across. Okay. All right. Questions on that example? So on any set, you can really, there's a partial ordering of sets, like containment is a partial ordering. We'll talk about the difference between a partial ordering and a total ordering, like really soon. And some, like all total orderings are partial orderings, but not all partial orderings are total orderings. So containment is a partial ordering. And here's another kind of example that I think we'll have some familiarity with. We just look at the set of real numbers. And so if x and y are real numbers, we could define the relation by saying x is related to y if x is less than or equal to y. Is this a partial ordering? There's very little space that I allowed for this because it really doesn't take much to show that it's a partial ordering. So is it, we could show that it's reflexive. I mean, this is going to be a one-line proof. What is it that we're going to say that to show that it's reflexive?
X is equal to Y, and they're reflexive, basically.
Well, we don't take two different elements when we talk about reflexivity. Like, reflexive means everything's related to itself. So if I just take any old real number, like if x is a real number, how do I know it's related to itself? How do I know x is related to x? How is this relation defined?
It's defined by, okay, so I would say it is reflexive because it's a greater than or equal to value, which means that x and y could
Yeah.
be the same value.
Right. It's less than, but yeah, less than or equal to, right? So yeah, because x is certainly less than or equal to x for all real numbers, x. It's equal to it, right? It's an or equal to, so we get to write that for any real number. Antisymmetry. So with antisymmetry, we suppose we have a relation going both ways. Like we have a couple of elements, x and y. So if x is related to y, meaning if x is less than or equal to y, and y is related to x, and y is less than or equal to x, what does that mean?
Means that any instances of symmetry, Y equals X.
Yeah, like if x, like just think about the real numbers, right? Every number has a spot on the real number line. So if x is less or equal to y, that means x has to lie to the left, either be in the same location or lie to the left of y on the number line. And if y is less or equal to x, same thing. They're either occupy the same spot or maybe y is to the left of x. So if both of these are true, if x is less or equal to y and y is less or equal to x, the only way that happens is that they're the same number. If I have both of those inequalities, it forces them to be the same real number. And then the last thing to check is transitivity. Is it transitive? Well, let's suppose x is less than or equal to y and y is less than or equal to z. If x is less than or equal to y and y is less than or equal to z, then yes, definitely x has to be less than or equal to z. That forces that to be true. So it is transitive. This is a partial ordering.
Isn't that like symbol ordering?
So this little symbol, that one?
Yeah.
That means for all. Sorry. For every or for all. And also while we're at it, I might use this notation a little bit. A backwards capital E means there exists. This sense of ordering and is so common. A lot of the time we might just use a less than or equal to sign symbol to represent instead of calling it capital R, if it's an ordering, like a partial ordering or a total ordering, we might just use the less than or equal to sign on anything that is a partial ordering or a total ordering. There might be some practice exercises where that happens. Just be careful when you read the problem. Make sure you understand what the set is and how they're defining the relation. It might not be real numbers, and it might not be the usual sense of less than or equal to, but they often use that symbol as to just denote the relation. Okay. Now, these two examples that we looked at, the sets and containment, defining that, partial ordering that way, and then real numbers and like less than or equal to. They're pretty similar, although they're different in a really important way. So on the next page, we have another definition. So suppose we have a partially ordered set, meaning we have a set with a partial ordering relation. Two elements of a set are called comparable if one of these is true, right? If either A is less or equal to B or B is less or equal to A, or related to, I should say, if A is related to B or B is related to A, doesn't matter what direction, if one of those is true, we say that pair, they're comparable. For example, if I have a set that's just all the positive divisors of 30, and we're going to define this partial ordering, which again we're just going to denote with a less than or equal to sign, and we say that M is related to N if M divides N. And M divides N means M is a factor of N. We're going to figure out which pairs are comparable. So 15 and 5, they're in the set because they're two positive divisors of 30. Are they comparable, and how do we know? Can we say that 15 is related to 5 or that 5 is related to 15? Is one of those going to be true?
Would 5 be related to 15 because it multiplies by 3?
Right, it's a factor of 15. Yeah, so these are comparable. So yes, because we would say 5 is related to 15 because 5 is a factor of 15, or 5 divides 15. 5 and 6 are also positive divisors of 30. Are those comparable?
Okay, so the position doesn't matter at all.
Yeah, two elements are comparable if we just have the relation going in one way or the other. Regardless of the order, if we could say one is related to the other, then they are, then they're comparable.
Okay, that's what I was hung up on, because I was like, 15 doesn't divide 5.
Right.
The way you read that.
Mm-hmm.
That's the way we read it.
Right, but comparable just means if you have the relation going in one direction or the other.
Gotcha.
Yep. 5 and 6 are both positive divisors of 30, so they're in the set T here. Are those comparable? No, 5 doesn't divide 6, and 6 doesn't divide 5. So what it means, if you have a partial ordering, if it's the case that all pairs are comparable, that no matter what two elements you pick, you can always say, oh, one is going to be related to the other in one order or the other, then we say it's a total ordering. Look at the last example again with the real numbers. This is a total ordering because No matter what two real numbers you pick any two real numbers you want, x and y. Either x is less than or equal to y, or y is less than or equal to x. And we'll just note that the or equal to part is crucial there, because otherwise, if you pick the same real number, then it's not comparable to itself. But that would be a total ordering. This, the first one, not a total ordering. Not every pair is comparable, and we could see that at play right here. Oh no, not there. Hold on, I take that back. We could see that at play. I'm going to come up with another example. If I take the two subsets, I don't know, 2, 3, and 1, 2. Neither of those sets is a subset of the other, so they're not comparable. So this containment relation, this partial ordering that we defined first, is not a total ordering. That's an actual partial ordering. When we looked at these, the real numbers, and we said x and y are related if x is less than or equal to y, that's a total ordering. And a total ordering is also called a chain. And it's, take the real number line, like that's a chain, right? Everything has a spot on the chain. Total orderings are really easy to visualize. It is literally like a single line, and everything has a position on it. Partial orderings are harder to visualize, but we do have a nice way to do it. Oh, here we go. This example 127 is the same thing as the real numbers. I just defined the same relation on the integers instead of the reals. But this is a partial ordering. In fact, it is a total ordering. We've already shown it's a partial ordering because everything we did for the real numbers holds for the integers here. And basically, we just want to make the observation that for any two integers we pick, then either x is related to y or y is related to a, right? X is less than or equal to y, or y is less than or equal to x must be true. Like one of them has to be the case. And so that means that this, the set of integers, along with this partial ordering, is in fact a total ordering. If we take the one that we did before when we looked at the divisors of 30 and said defined a relation by saying m is related to n if m divides n, that is not a total ordering because look, not all pairs are comparable. 5 and 6 are not comparable. We still can have a nice way to visualize a partial ordering, and we're going to draw what we call a Hasse diagram for that relation. There is sort of elevation, like there's kind of a hierarchy. Yep. Mm-hmm.
Thank you.
Mm-hmm. So there's like a kind of a vertical hierarchy in a Hasse diagram, but basically each element of the set that you're working with is kind of has a location, like a point, and we if like A is related to B, then B appears above A, and we draw a line between them. So in this set, with the positive or the divisors of 30, we had 1, 2, 3, 5, 6, 10, 15, 30. Are those all of them? I think those are all the divisors of 30. So I'm going to put 1 on the bottom. Now 1 goes into everything, right? 1 divides everything, but if 1 divides 1 divides 5 and 5 divides 10. So I'm actually not going to draw a line from 1 to 10. Like that's going to actually just exist by drawing by forming kind of a, I don't want to use the word chain because that it invokes like a total ordering, but just by following the path. So from here I'm going to use just the primes. So I'll put 5 here, 2 here, and 3 here. It just looks, the whole diagram looks a little bit better if I put 5 in the middle. And now I put the primes there because nothing can go in between, right? We draw a line from 1 to 5 because 1 is related to 5 and 1 isn't related to anything in between. Now 2 and 5 are both related to 10 because 2 divides 10 and 5 divides 10. So I'm going to put 10 over here. And now I know that 1 divides 10, and that's already, that's conveyed here by like that path and also by that path. I'm going to put 15 here because 15, 3 divides 15 and 5 divides 15. Two and 3 also divide 6. But 6 doesn't divide 10 or 15. So I'm just going to kind of put 6 in the middle. I need to be able to draw a line from both 2 and 3 to 6. It's okay for the lines to cross. And then 30, right? 10 and 15 and 6. There's nothing in between those values. So I'm going to draw those directly. And there's a Hasse diagram that conveys that partial ordering.
Is it just coincidental that that turned out to be a cube, or?
Well, it had a lot to do with where I chose to put 2, 5, and 3 in the beginning. Like a lot of the time there might be like a nice kind of symmetry and figure that emerges. But if I had done like 2, 3,
I get that if you had
5.
put numbers in different places, it wouldn't look like a cube. The
Yeah.
graph would still be a cube, but.
Yeah, it wouldn't really look like one, but yeah. I mean, I guess
It's a coincidence of the relationship at hand.
I think so. I mean, you often get like nice visual symmetry that happens, whether it's a cube or something else like that. That could, that's not uncommon if you kind of arrange your elements in a clever way. Other questions? Okay. All right. Let's take a little while and talk about equivalence relations. We definitely are not going to finish this section, but we'll get a little start. So a partial ordering was a special kind of relation. It's, reflexive, antisymmetric, and transitive. If we just switch one of those and say instead of being reflexive, antisymmetric, and transitive, a relation that is reflexive, symmetric, and transitive is an equivalence relation. So if everything's related to itself, if you have symmetry, and if you have transitivity, then your relation is an equivalence relation. Let's do an example. We're going to define a relation on the integers, and we're going to say that two integers, a and b, are related, like a is related to b in that order, if a minus b is a multiple of 5. Like if you subtract them and it's a multiple of 5, they're related. Let's just play around with this relation, get a sense for what it means, and test out some ordered pairs. So is 7 2 in the relation? Is 7 related to 2? And if I'm going to check this, I'm just going to go use the definition. I'm going to do the subtraction. 7 minus 2, this is equal to 5. And yeah, that's 5 times 1. That's a multiple of 5. So that means 7 is related to 2. Let's do another one. Negative 11 and 4. Well, negative 11 minus 4 is negative 15. And that's a multiple of 5. It's 5 times negative 3. So this means that negative 11 is related to 4. It's related to 4. Let's see if it's related to negative 4. If we do this subtraction, negative 11 minus negative 4. So we're going to add 4. That gives us negative 7. That is not a multiple of 5. So that means that negative 11 is not related to negative 4. For negative 21. Again, just going to do the subtraction. Minus a negative 21. That's plus 21, so that's 25. That's a multiple of 5. If I'm checking, when I'm checking to see what's related to what, I mean, I feel like I definitely do like to repeat myself, but I have to go back to how the relation is defined. So each one of these was a simple, just check, do the subtraction, and do a quick check. I could see if these are related. We saw that 4 is related to negative 21. Do you think negative 21 is related to 4? What happens when you reverse the order of subtraction?
It still works out negative.
Yeah.
It won't work out for all of them.
Well, let's...
I guess,
Yeah, so you said that if we do negative 21 minus 4, we just get negative 25, right? Okay, so that's 5 times negative 5. That works. You said it might not work out for all of them, and then you said, oh, well, maybe it will. What do we think?
like I looked at
Can you turn your mic on?
Sorry,
Yeah.
turned it off.
Okay.
Yeah, because I looked at 7 too, and I guess if you reverse those, it'd be negative 5.
What happens when you reverse the order of subtraction? In general? Like, if I compare A minus B to B minus A, how do those results compare?
Signs will be different.
Signs will be different. In fact, that's the only thing that changes, right? And if the sign is different, does that affect whether or not it's a multiple of 5? No, it's just a negative multiple or a positive multiple, right? Still a multiple. So it looks like, we have a strong hunch that this relation is probably symmetric, it sounds like. In fact, we're going to show it. And I think that this next example, we're going to prove that this is an equivalence relation. It's probably a good one to end on for the class, so it'll take a little while to do. We're going to show that this is an equivalence relation. So the first thing I think I'll do is just rewrite it. So the relation from example 129, this said that A is related to B. If A minus B is a multiple of 5, so we're going to show it's an equivalence relation. That means we're just going to show that it's reflexive, that it's symmetric, that it's transitive. I'm not...
Quick question.
Yeah.
Before you start. You wrote for some k within z.
Mhm.
Did you write for all k within z, or does that mean something else?
No, it means something. For all k and z, that means that no matter which k I pick, it's that multiple. It's not... So A minus B isn't going to be every multiple of 5. I could write, actually, so what I could do is I could say there exists an integer, k, such that A minus B is equal to 5k. It's just an existence statement, that it is some multiple of 5. If I said for all k, that would mean that it's every multiple of 5, and it can't be more than one multiple at a time. So let's start with reflexive. To show something's reflexive, you need just grab one arbitrary element and convince the reader that it must be related to itself. Don't be particular about, don't pick an actual integer, but just say, let's let x be in z. We want to answer the question, is x related to itself? And to answer that question, we have to go back to how the relation is defined. So in this relation, I'm just going to look at x minus x, right? I have to look at, to see if something's related to something else, I'm just going to subtract them and see if I get a multiple of 5. Well, x minus x is 0. And 0 is 5 minus 0. 0 is definitely a multiple of 5. So so R is reflexive. Everything's related to itself. If you're going to show something symmetric, you need to grab two arbitrary elements, right? Because this has to do with being able to reverse the order of the relation. So we'll let x and y be elements of z. And we suppose that x is related to y. We want to answer the question, is y related to x? This is the one that we kind of developed a hunch about on the last page, right? It looked like if we did the subtraction, all we would do is change the sign. So what we have to go on is that x is related to y. So let's write that. Since x is related to y, that means that if I subtract them, x minus y, I must get a multiple of 5. So x minus y is equal to 5k for some k and z. If I want to know if y is related to x, what is it that I want to look at? What is it I need to check?
If y minus x is equal to multiple of 5.
Yeah, if y minus x is a multiple of 5. So let's observe y minus x. What did we say? What did we notice before? Like, what's the only result when you reverse the order of subtraction?
Sign change.
The sign change, yeah. Y minus x is the negative of x minus y. I mean, you could check, right? If you distribute that negative, you'll get the same thing. You get it right back. So this is negative x minus y, and this is negative 5k. And then the only thing I'm going to do to wrap this part up is I want to write it as a multiple of 5 and not a multiple of negative 5, so I'm just going to write it as 5 times negative k. That's a multiple of 5. Right, since negative k is in z, then y must be related to x. So it is symmetric. I'm not going to bother checking antisymmetry because that's not involved in the definition of an equivalence relation. I just need to show reflexive, symmetric, and transitive. So let's move on to transitivity.
Quick question before
Yeah.
we move on. With the different symbols, there's like, we have R for real numbers, then we have Z, and then we have Z plus. So Z is just positive integers.
No, z is all the integers.
Z plus is all positive.
Yeah, z plus is all positive integers. They're the same as the natural numbers.
Okay, what's the difference between the R and the Z then?
R is all real numbers. So if I draw a real number line, here's 0, 1, 2, -1. So Z contains these guys, right? And so on. R contains all of them. Pi is a real number, but it's not an integer, for example. The square root of 2 is a real number, but it's not an integer.
Okay, so whole numbers versus like doubles.
Whole numbers versus, I don't know what that, I didn't catch the last word that you said.
That's the programming in doubles, so like.
Oh, I understand, yeah. Yeah, yep. In fact, so it's just the the positive and negative whole numbers together with 0. Those are the integers. So let's see, to show something is reflexive, we need to just grab one arbitrary element, show it's related to itself. For symmetry, we had to grab 2 arbitrary elements and show that if we have the relation going in one direction, we got to have it going in the other. For transitivity, you need 3 arbitrary elements. We're going to let x, y, and z be integers. And then we're going to assume that we have a couple pairs of relations. So let's suppose x is related to y, and y is related to z. What would have to be true if this relation were transitive?
X would have to be related to Z.
Right, right. So we're going to answer the question, is x related to z? Oh. These should be r's, not z's. Relation. This r is not the real numbers, right? This is just a regular capital R that we're denoting as the relation itself. That contrast that with this R, that's the set of real numbers. So we have a couple of things. We have this and we have this. We have both of those for free. Let's see what they get us. Since x is related to y, I'm going to go back to how the relation's defined. If x is related to y, that means that x minus y is a multiple of 5. So I use that part of the given, the supposition. What about this part? What can I say if y is related to z?
That y minus z equals 5k for some k easy.
Yeah, only I'm not going to use k. I'll call, I'll use j, but you could use something else. I don't want to assume that it's the same multiple of 5, so I don't want to use the same letter. But just, 5 times something, that's an integer.
But the inference there is that both x and z are factors of 5. Forgive me if I got the wrong word there.
I don't think, no, x and z are probably not going to be x and z need not be factors of 5. We're going to show that, x is related to z. Yeah. Yeah, x minus z is a multiple of 5.
Thank you.
Yeah. So in order to see, so if I'm checking the part that I highlighted in blue, right, what is it that I want to look at? How do I see if x is related to z, or what would it mean to say x is related to z?
That x minus z is 5 times a constant number.
Right, so I'm gonna, what I want to do now is just play around with the expression x minus z. I can't say right now it's a multiple of 5, right? I have to show it. But that's what I want to look at. And so I'm going to be a little bit clever here. X minus z is x minus z. And I'm going to pull one of the oldest tricks in mathematics. I'm going to subtract and add the same thing. I'm going to subtract y and add y. I'm allowed to do that. I've just added 0 to this expression. But I'm going to kind of choose to organize the expression in that way. I want to group the terms like that. What's helpful about that?
You can substitute them for the 5K and the 5J.
Yeah. So this is 5k plus 5j. What am I going to do now?
You're gonna pull the placement.
Yeah. Yep, exactly. Now there's one small formality here, one small detail, I guess, that we want to tie up. And that is just to state, and it's true, I mean, if k and j are integers, then k plus j has to be an integer. But that's important, right? Because 5 times 2/5 is 2. That doesn't mean that 2 is a multiple of 5, right? It's really, what's important is that I was able to multiply it by something that is just an integer. So since k and j are integers, then k plus j is an integer. And so that means that x is related to z.
You mean R?
No, it means x is related to z, so the pair xz is in R, is in the relation. Yep. And then, you know, just a nice concluding statement. So we showed that it's reflexive, symmetric, and now we just barely finished showing that it's transitive. So something like, having shown that R is reflexive, symmetric, and transitive, follows that R is an equivalence relation. And that takes us pretty much to the end of our time. We're going to look more at equivalence relations and then seeing some cool things that happen when we have an equivalence relation. We'll probably finish up this section on Wednesday. Today's Monday. So let me know if you have questions. I should have your assignments graded by Wednesday. That's my goal. And we're working on assignment 2. So if you have any questions on those, please ask during class, or email or text is fine too. Thanks, everybody.